Hello students, welcome to third lecture of competitive chemical bonding and molecular structure. In previous lecture we discussed about some examples which you may find difficult. Now let's talk about some more questions. So as the first question suggests, electron identified by quantum numbers and n and L are mentioned, and we have to arrange them into increasing order of their energy. So same type of question was discussed earlier. We have to use n plus L rule for this. So n plus L value for this it will be 5, n plus L for second it will be 4, for third it is again 5, and fourth question it is 4. So now question is, here we have 2 5 and 2 4s. So how can we find lower or higher energy orbitals in them, because they have same n plus L value. So when you have same n plus L value, then you have to concentrate on n value alone. That means if we talk about the second and fourth, then we have n is equal to 3 and n is equal to 4. So from that we can say that lowest energy orbital will be n is equal to 3, n plus L 4. Then second one will be n is equal to 4, n plus L 4. Then next n is equal to 3, n plus L 5, and then n is equal to 4. So our answer will be option A, 4 2 3 1. That means first you have to find n plus L values. Then if you find similar n plus L value, then you have to concentrate on n values alone of that same or similar n plus L values. Then arrange them into their increasing order. Now let's talk about the question like this: number of water molecules is maximum in 18 grams of water, 18 moles of water, 18 molecules of water, or 1.8 grams of water. Now if you have this type of values, then convert them into similar values. Either convert them into grams, or convert them into number of moles, or convert them into moles or molecules. So let us start with converting each values into grams, because first and last values are already in grams, so we have to convert only two of them. So we know that 1 mole of water is equal to 18 grams. That means 18 moles of water is equal to 324 grams. Then 18 molecules of water. So obviously 18 molecules of water has extremely low number of mass, because 1 mole is equal to 18 grams, and we know that 1 mole is equal to 6.022 into 10 raised to 23. That means if you want to convert the grams, this value into grams, then you have to divide 18 with Avogadro number, 6.022 into 10 raised to 23. So obviously this will be lowest possible value, and last value is 1.8 grams. Okay, so 18 grams, 324 grams, 18 divided by 6.022 into 10 raised to 23 grams, and 1.8 grams. So obviously maximum number will be in 18 moles, because it has highest number of grams. Next question: the variation of boiling points of hydrogen halides in the order of HF is greater than HI, is greater than HBr, is greater than HCl. What explains the higher boiling point of hydrogen fluoride? So 4 points are mentioned. So obviously we know that in remaining 4 options we have intermolecular attractive forces, and this type of and the type of these forces will be dipole, because hydrogen and halogens have comparatively very much larger gap of electronegativity, and that's why they will be polar by nature, and one polar molecule will attract second polar molecule via dipole interaction. But in HF we have specific type of intermolecular attraction which is called hydrogen bonding, and because of hydrogen bonding obviously it will attract second molecule strongly, and that's why it will be comparatively higher in boiling point. So answer will be D. There is a strong hydrogen bonding between HF molecules. In remaining molecules you will have dipole attraction. Next is arrange them these pairs in proper manner. So you have to arrange this according to their repulsions, because we have electron pairs, two type of electron pairs, lone pair and bond pairs. So as we know, lone pairs are located at the single atom, while bond pairs will be shared pairs, so it will be comparatively away from the nucleus, and lone pairs are comparatively closer, and that's why they will repel strongly. So repulsion between two lone pairs will be highest and repulsion between two bond pairs will be lowest, and bond pair and lone pair repulsion will be in between. So you have to arrange them as per this order. Lone pair repulsion will be highest, then lone pair bond pair, and then least repulsion will arise in bond pair bond pair. The next question is about the hybridization. So we already discussed about how to check hybridization, so try to find answer yourself, and if you find any difficulty feel free to ask, we will discuss it in detail. Then next question, which of the following species is not paramagnetic? Now we can check for O2 and B2, it is already mentioned in our textbook, but what about NO and CO? To find their magnetism, first we have to find their orbital diagram, molecular orbital diagram. And MO diagram of NO and CO is in our discussion in upcoming points. Okay, so we are going to discuss in detail the MO diagram of NO and CO. That means these are heterogeneous diatomic molecules. It contains two different atoms. And in textbook we discussed about homogeneous diatomic molecules only, that means N2, O2, etc. And in this case we have two different atoms. So we will discuss about their molecular orbital diagrams in detail, and then you can solve this question yourself. So that means we are not going to discuss full NO and MO because of this question, but description of NO and CO diagram will answer this question as well. So let's jump to the last question, which of these following hybrids has largest bond angle? So notice here we have S, Te, O and Se, and all of them belongs to same group 16 or oxygen family. So they belongs to same group, that means their electronic configuration will be similar and hybridizations will be similar as well. So only difference will be is their sizes. So you have to arrange them into increasing order of their sizes first, and then smallest ion will have largest bond angle and largest ion will have smallest bond angle. But why? So from that point we can say that oxygen will have highest bond angle because it is smallest in size. But why? So reason is because of smaller size electron pairs are comparatively closer. So let's compare with two different atoms. Suppose this is oxygen atom and suppose this is a tellurium atom, size of tellurium, the largest from given 4. So what happened when we place electron pair, two electron pairs in both of them? Now let us assume between two electron pair there is some minimum distance must be obtained, otherwise it will be highly repulsive. To stabilize the atom or molecule, certain distance is necessary. So let's say we need 10 pm distance at least. You cannot reduce distance between two electron pairs than 10 pm. Okay, this is just assumption, assumed value, and now let's zoom in our structures. So at the center we have oxygen, at the surface we have tellurium, and this is these are the nucleus of both of them, that means center of these spheres. So let us say this is the minimum distance 10 pm. Okay, so we have to maintain this distance at least. So where this falls in both of them? Okay, so that means if two bonds are present in oxygen, then this will be the bond angle, and if two bonds are present in tellurium, this will be the bond angle. Okay, so obviously you can see the difference. Bond angle in oxygen is comparatively very high than the bond angle of tellurium. So as the size increases, there is more space to be occupied by electron pairs, and they can go far away without increasing bond angle much. But if you have smaller size of atom at the center, then electron pairs have very less space available and that's why bond angle will be comparatively higher. So simple thing, when you have similar group elements, then smaller sized atom will have larger bond angles and larger sized atoms will have smaller bond angles. So size of H2O will be smallest, so it is smallest. Then we have H2S on second number, then we have H2Se on third number and H2Te on fourth number. Okay, so this is the increasing order of their sizes, O, S, Se and Te, and same will be the decreasing order of bond angle. That means bond angle will be highest in oxygen, then we have S, then we have Se, and least bond angle will be in Te. Okay, so increasing order of atomic sizes will give us decreasing order of bond angles. Now in next lecture we will discuss about the molecular orbital diagram of NO and CO, that means heterogeneous diatomic molecules. If you find any difficulty regarding to these points, or if you have any other questions in any of the reference books or even in textbooks, feel free to ask. We will discuss them in detail in our upcoming lectures. Thank you.